Today we're going to talk about section 2.6, graphs of basic functions. We have the list of 7 functions we are going to talk about. These are often referred to as parent functions, and where we're going with this in the next section is to learn graph shifting techniques and reflection techniques, and we can start by using these basic functions and then shifting them around up, down, left, and right, flipping them over the x and y axis. So we need to learn the shapes of their graphs, their domain and range, intervals of increasing and decreasing, and any discontinuities. So let's start with defining continuity. A function is continuous on an interval if for any value on that interval the output exists. So that simply means that the x value is in the domain, and that's what we're saying right here. This is the symbol for contained in, and then capital D meaning domain. So if we take a look at the function 1 over x squared, there's a discontinuity at x equals 0 since 0 is not in the domain. Since 0 is not in the domain, that means that f of 0 does not exist, and the graph is not continuous on the entire interval from negative infinity to infinity. There is a discontinuity at x equals 0. In this next example, we have x squared minus 4 over x minus 2. If we look at a graph of this, it's going to look like a linear function with one key difference. At x equals 2, there's an open dot signifying discontinuity. And if we look back at the original, if we attempted to substitute 2 into the original, we would have division by 0. 2 is not in the domain of that function, and therefore on all real numbers this function is not continuous. Its domain is negative infinity to 2, not including 2, union 2 to positive infinity. The book gives more of a description of continuity. It says it's an informal definition. The function is continuous if you can draw it without picking up your pencil. So I've needed to give you guys something that's a little more technical than that. And let's go down and take a look at these functions. The book has them already nice and neat and plotted in with the domain and range. So we're going to take a look at each of these out of the book rather than me sketching them. This is the identity function, and that's f of x equals x, which is just a linear function with slope of 1 and intercept of 0. And that means if you choose an x value, you get the same y value. The domain and range are both all real numbers, and as we can easily tell from the graph, it's increasing on the entire domain, and there are no discontinuities. F of x equals x squared. It's called squaring function. If it were ax squared plus bx plus c, we would call that a quadratic function. We talk about those in section 3.1. But x squared makes the shape of a parabola, and the domain is all real numbers. The range is 0 to infinity, including 0. There are no discontinuities, and the graph is decreasing from negative infinity to 0. It changes direction at what is called the vertex, and then begins increasing from 0 to infinity. F of x equals x cubed, which is called the cubing function. Domain and range of all real numbers, no discontinuities, increasing on its entire domain. The square root function does not have a domain of all real numbers, so we're looking up here at the square root function. We can't have a negative under square root. Square root of 0 is 0, so 0 is okay. The domain is 0 to infinity, including 0. If we go any less than 0, we'd have a negative under square root, which is not a real number, and we are working in the real number plane. So when we take all of the valid inputs, which are elements in the domain, run them through the function, the range is going to give us positive numbers including 0. And I recommend at this point in time we're thinking about range by examining the graph and looking at the y values more so than algebraic computation. Square root of x is strictly increasing on its domain, not including 0, and it is continuous on its entire domain, so there's no holes in the graph over here. Now remember, a discontinuity is not, we can't say it's discontinuous over here in negatives. Negatives aren't part of the domain, so it's on an interval from A to B if there was a value in between that caused a discontinuity. So the cubed root function, the domain of the cubed root function is all real numbers. So remember, the cubed root of a number, a negative has a cubed root and a positive has a cubed root. So unlike the square root, we can have negatives under a cubed root. So for example, the cubed root of -8 is -2. This function is strictly increasing. There are no discontinuities. Domain and range are both all real numbers. Then we've got the absolute value function. The absolute value function looks like a V on the graph. It looks like the identity on the positive side, and then it's y equals -x for negative x values. So absolute value decreases on the left-hand side from -infinity to 0. It increases from 0 to infinity. The domain is all real numbers, but as you know, when you substitute in any x value into absolute value, you always get a positive number or 0, so negatives are not in the range. There are no discontinuities. And then we have the greatest integer function, which might look a little more complicated than it really is. The domain is all real numbers, and what the greatest integer function does is pairs every real number with the greatest integer less than or equal to x. So for example, right here, if you take a look at pi in the greatest integer function, it's going to pick the greatest integer less than that value. So pi run through the greatest integer function is just 3. I do not suggest using 3 as an approximation for pi, but if that were the input into the greatest integer function. So this looks like steps on the graph. If we take a look, let's look at x between 2 and 3. So x between 2 and 3, no matter what value of x between 2 and 3, the greatest integer function is going to output y equals 2. And then once we get to 3 exactly, that's when the greatest integer function then takes another step up to y equals 3. So we do have those discontinuities at each next integer. So the range is the integers. And you can see that this function is constant on each one of those intervals. It's not increasing or decreasing, so on each interval we're constant, and then we have discontinuities at all integer values, so that's the open circles. Okay, the next thing we are going to talk about is called a piecewise defined function. A piecewise defined function gives you a condition on the domain, in which you will then choose which piece of the function to plug in the element of the domain. So this example, f of x equals x squared if x is greater than or equal to 1, or 3x if x is less than 1. We want to think of it as this column right here gives us a condition, and if I were to translate this as in an English sentence, I would say if x is greater than or equal to 1, then f of x is x squared. Then this line would translate to if x is strictly less than 1, then f of x is 3x. So rather than just having a one piece, we have two pieces in this one, you could have three pieces or whatever, you have a condition on the independent variable. So let's answer these questions. Let's evaluate the function for f of 0. Now, the independent variable value is 0, so that fits into the condition that 0 is less than 1, which means that the output we need to use is 3 times the independent variable value. F of 4 fits into this condition. 4 is greater than or equal to 1, so the output needs to be plugged into the square function. And when x equals 1, that fits into this top piece. 1 is greater than or equal to 1. So we choose the top piece, so 1 squared, which is 1. Let's do maybe f of -5. -5 fits into this condition. -5 is less than 1. So we will use the output 3 times -5, which is -15. We can graph piecewise defined functions. We don't spend a ton of time graphing them, but what you would do in this case, if you have x squared, for x greater than or equal to 1, is graph this parabola for all values of x greater than or equal to 1, and then graph this line, 3x, for all values of x strictly less than 1, and then you would have the piecewise defined function graph.